So this is going to talk about, we're going to talk a lot about the properties of water, pH, salinity, that kind of stuff. That's going to really be the focus of this module. So let's go ahead and get started. So let's talk about the properties of water. Water floats as a solid. This is kind of a big deal because if you think about it, most things are more dense as a solid, and so they sink. So that's super huge, and I'll explain that in a second. It absorbs and retains heat really well, and so the temperature is not going to change very quickly. You may notice, like, say you have a swimming pool, it takes a while. It can be even cold at night for a little bit, and it takes a while to kind of cool, for actually the whole pool to cool. But it also, in the same vein, if it's really cold, it takes a little bit for it to heat up too. Water molecules stick to each other, which is known as cohesion, and they stick to other polar substances, which is adhesion. And I'll talk a little bit about that too. So first, let's talk about how important it is that water floats as a solid. And I'm not going to lie, when I first heard this, I kind of was like, okay, yeah, whatever. Ice floats. I've noticed that my whole life when I, drink an icy drink. What's the big deal? So let's talk about it. Let's say this is our body of water. Okay. Currently, what happens is when it freezes over the top and you have this thin layer of ice, right? So since you have this thin layer of ice, all these critters, it's cold underneath, but, they're still, allowed to kind of live their little sea critter life or, pond critter life. But now let's think about if water did not float as a solid. Okay, so what would happen? That first layer would freeze and it would sink to the bottom, right? Then you'd have a next layer that would freeze and it would sink to the bottom. And then you'd have another layer that would freeze and it would sink to the bottom. And then the next layer and it would sink to the bottom until your entire pond was frozen, which means that your critters that were living in that pond couldn't live there anymore, or your ocean or whatever. Okay, so every winter, basically, any body of water would just become, one solid brick of frozenness, and you wouldn't have, any life underneath, right? You wouldn't get that really nice, basically little area for them to live. If you think about icebergs, right? Instead of having an iceberg floating like this, right? Your iceberg would sink to the bottom and fill up the ocean. Okay. So that's a huge problem, right? Especially since the bottom of the ocean is really cold. All of that ice might just, keep, filling up the ocean, basically. It's really a big deal in ponds. But anyway, that's why it's so important that water floats as a solid. That's super important. The other part, let's change color here. Water is a polar molecule. So what does that mean? So what is water? Water is H2O. So we have an oxygen molecule, and then we have two hydrogens, right? Now, hydrogen is a positive, right? So like this part of the molecule is like a little bit positive, and this part of the molecule is a little bit positive, and then this part is a little bit negative. Okay, and so what that means is that this side of the molecule is a little bit negative, and these parts of the molecule are a little bit positive, and that's what it means when a molecule is polar. Okay, so but also, let's say we have another water molecule hanging out here, right? Because they're usually not alone. Again, maybe this H is a little bit positive, this H is a little bit positive, and this is a little bit negative, right? So what do we have going on here? Well, that means, let me get another color. That means that this side is going to be attracted to this side, right? And so they're going to be, they're not going to be bonded together, right? They're still going to be separate water molecules, but, the O's going to be like, hey, and the hydrogen's going to be like, hey, and they're going to enjoy, kind of want to hang out together. Okay, and so that's that cohesion, right? They're kind of sticking together. They're basically sticking together. Okay, and then you might have another hydrogen over here sticking to this one. And then you might have, another hydrogen over here sticking to that one. Okay, and that's what's going on there. If you've ever seen like a cup of water, okay, if you fill up your cup really, 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 really high, sometimes you get this little like bubble that kind of sticks out over the top, right? And it's over the top of your cup, but it hasn't spilled yet. And the reason for that is because the water is sticking to itself and it doesn't want to let go. Eventually, if you keep pouring water, it will spill over because, these aren't bonds, right? They're just kind of like hanging out together things. They kind of like, hey, we want to stick together, but we're not like super close. If you think about like those like removable stickers that are like decal kind of things, it sticks, but it's not gonna, you can still pull it off. So that's kind of what's going on here. They're little bonds that kind of stick together. So anyway, that's how water, these are really kind of special things about water that a lot of other molecules don't have. So it helps kind of lay the groundwork for why it's so useful and why it's kind of this universal solvent, this really special thing. So now let's talk a little bit about the water cycle. You don't need to know like super details about the water cycle, but you do need to know that water is stored in the ocean. We can have surface runoff. This is a big problem. We talk about this a lot in environmental science, actually, because anything that we do on the surface can run off into the oceans or in bodies of water. We do get evaporation from the ocean. And this is really any body of water, which is really a big deal. If you've ever, let's see if I can draw here. Yeah. If you've ever had like a fish tank, a saltwater fish tank, you may notice that the water in your tank goes down, but the only thing that evaporates is the water. So you may even see like when I had a saltwater fish tank at school, you would see like a little bit of kind of salt right here that would kind of gather around the edges. And that was because the water was evaporating, but not the salt. So the water would get saltier and saltier and saltier. And so when I added water to my fish tank, I would add fresh water, not salt water, because I didn't want to get even more and more salty. Okay. So that's really important. And that's something that we also talk about in environmental science, because like even fresh water has some salt in it. And so as it evaporates, it leaves behind salts, which can make the ground a little more salty. You can have water stored in the atmosphere. We have like basic like gas water that's in the atmosphere. And then again, it comes down as ice and snow. That's precipitation. And then, it runs off. So let me it runs off. It gets stored in the ocean. It evaporates or it evaporates again. And then it's stored in the atmosphere and then it precipitates. And so this is kind of like the basic, um, the basic water cycle. And then of course you have some that infiltrates into the groundwater, and that's kind of where we drink and stuff like that. But this is kind of like a basic of the water cycle, a basic kind of idea of it. Okay, let's go some more. Okay, the salinity. So the big thing is fresh water can still be a little bit salty. And when we say salt water, we're not saying NaCl water. We're not saying table salt water. We're saying that it's basically got salt ions in it. So like ocean salt water, sea salt has all of these things in it. Okay, so it is not table salt water. it is salt because it's got these ions in it. Okay. It does have chlorine, which is, Cl, and it does have sodium, but it also has potassium, calcium, sulfur, magnesium, and some other things in it. So, for example, when if you purchase sea salt to put in your food, you're not putting NaCl in your food. You're putting basically evaporated ocean salt, which is all of these things in your food, versus, if you buy table salt, it's NaCl. The other thing is that even fresh water has a little bit of salt in it. Okay, so basically something is considered fresh water if it's like less than or equal to like 5 parts per thousand of salt in general. So, even if you have something that's 5 parts per thousand, that's still considered fresh water, but it's got salt in it, right? It's got this stuff in it. So, even, super fresh water still has some of this stuff in it. So that's why when we talk about evaporation, you're still going to have this. Brackish, if we want to talk about brackish or like, kind of that in between, I usually think about that as like 10 to 15 parts per thousand. It can vary a little bit, but when I think about that type of water, I'm thinking kind of around there, or like the water in an estuary. And then like full salt water, like the middle of the ocean, I'm going to think about 35 parts per thousand. Again, it can be a little, different from there. Some places might be, 37, some places might be 33 or 32, but basically in your mid 30s is what we would consider like full salt water. And then brackish is around 10 to 15-ish. And then freshwater is 5, and 5 or less. So you can see, when these animals, if you're used to 35 parts per thousand, you may be able to handle somewhere close to brackish. You may not, or you may. Freshwater is really going to cause some problems, because that's not what your body is used to. And this PPT means parts per thousand. So if we think about like a graduated cylinder, if we think like maybe we have like 1,000 mils, say this would be 1,000. And so the water is up to here. 35 of that would be salt, basically, in like salt water. So that's kind of how you explain that. So like 35 mils out of 1,000 would be like 35 parts per thousand. So that's kind of a little overview of salinity. Now let's talk about pH a little bit. This is the pH scale. A big thing to know about the pH scale is that it's a longitudinal scale. So from like 0 to 1 pH is like 10 times more basic than 0 pH, or like 13 pH is 10 times, or like 10 times less basic than 14. So each one of these is like, it's a log. So it's like times 10. Okay, so it's not 0 to 1 is not like a small amount. It's actually, times 10 each one. So like 0 to 2 would be like 20 times more basic. Or like, 7 to 5 is going to be 20 times more acidic. So it seems like it's, just a little bit, but it's actually a lot. Okay. Right neutral, super neutral, right in the middle, that's like distilled water. And distilled water is basically like water that they've taken everything out of. There's no salts in it. There's no nothing. It's like nothing, like 0 parts per thousand, right? If we're talking about salinity, it's very, very clean. And that's neutral. And we think about the ocean, we think, oh, the ocean is about neutral. Well, it's really not. It's a little basic. It's they say it's 8.1. I like to think about it like between like 7.4 maybe and like 8.1. So it's not exactly, 8.1 everywhere, but it's around in that range. Blood, again, 7.4. Blood and seawater are very, very similar. pH, um, you can think like liquid drain cleaner is going to be 14. Battery acid is like 0. Lemon juice is 2. Soda is 2.5. There you have like acid rain, clean rain. I don't know if you knew this, that clean rain is around pH 5.6. So actually clean rain on itself is still a little bit acidic, but it's not as, it's like a whole pH, almost and a half, more basic than acid rain. And again, that's, times to the 10. So that's kind of how pH works. And you guys have like a little lab with pH, but basically seawater is basically neutral, but it's just slightly basic. So I'm just going to write this here for you. Okay, let's go to the next one. Okay, so now we can talk a little bit about dissolved oxygen, because you'll see this a lot because it's super important in aquatic environments, freshwater and saltwater, because you need dissolved oxygen in order for these animals to survive, right? And so if you don't have dissolved oxygen, your animals won't be able to survive. So there's a couple ways that you can add oxygen to the water, mixing wind, waves, and currents. I don't know if you've ever, like, when you see like apartment complexes or places that have like fountains, the reason they have that fountain, right? Because the fountain is like, splashing water, is because when that water hits and it kind of disrupts the surface, it's basically oxygenating the water and adding oxygen to that water by disrupting that surface. And that's the point of those fountains. They're pretty, but they're also supposed to add oxygen to the water and kind of mix the water a little bit, even if it is just at the surface. Okay. Any photosynthesis that happens by anything in the water is also going to add oxygen to the water. Okay, so photosynthesis, this could be algae, microscopic algae. It could be plants, you know, any algae or seaweed that is not microscopic, anything like that. Animals are going to take oxygen out, and then decay of organic matter is also going to take oxygen out. And usually this organic matter, kind of floats to the bottom. It's like poop, dead cells, dead plants, dead animals, all that stuff on the bottom. And then you have these kind of bacteria and decomposers that are going to process that organic matter, and they use oxygen to do that. So usually this area right here where all this dead stuff is going to be low in oxygen because they're using a lot of oxygen. And that's why you need that mixing in order to not have, like maybe a surface zone where you've got some oxygen and then the bottom is anoxic, which means no oxygen and nothing can live on the bottom. You want to have that mixed. And so, that water that doesn't have a lot of oxygen is kind of, turned around. And so, you want it to mix. So that low oxygen water gets to come up here and get oxygenated. And then that high oxygen water gets to come to the bottom and add some oxygen. Because again, if you don't have oxygen at the bottom and it doesn't get mixed, eventually they're going to run out at the bottom and then the stuff won't decay and it's yucky. So you want your body of water to mix. And so again, that's one of the reasons they put fountains and stuff like that, and why like waves are so important, because if you have waves, you're going to, that's going to allow your water to mix, especially in these shallow areas, right? Because the waves kind of go like this and they're going to mix that water. Now, some more dissolved oxygen. Why do we care? What can fish survive in? What can they not? Less than 3 parts per million of dissolved oxygen, fish can't survive. It's just not enough. Okay, so down here, you're not going to have any fish. Okay, so if this is a body of water, let's say, where there's a lot of fish that people fish, commercially because they want to make money on it, if the dissolved oxygen gets too low, all their fish are going to die. They're not going to be able to make any money. They're not going to have a job anymore. 3 to 5 parts per million is like a 12 to 24-hour range of tolerance. It's kind of stressful, but they can kind of work through it as long as it doesn't occur for too long. Okay, about 6 parts per million, and the fish are able to reproduce. More than 7 allows them to grow and be active, and more than 9 supports abundant fish population. I usually like to think about 10. 10 is like this kind of ideal dissolved oxygen, 10 parts per million. And then we have this other image here that kind of shows in what parts per million do different animals live. So at 1 milligrams per liter, you're only going to get a brittle worm. You're not going to bristle worm. You're not going to get much at all. 2 milligrams per liter, you've got these spot fish. 3 milligrams per liter, you may have some crabs, maybe some anchovies. At 4, you'll get an alewife. 5, you're going to get a little more. And 6, you'll get like a striped bass. So that's just kind of an idea of what you get with different parts per million. But in general, I like to kind of think of 10 is that like, ideal parts per million for DO. And DO is dissolved oxygen, if you see that. So this is just kind of like the basics of the chemical oceanography module. Obviously, you should still read the content in the course. But this is kind of a good review if you're, studying for the exam, or you kind of watching this before the module starts. It just gives you kind of a good idea of what to expect for the module. And then when you read through the content, you're like, oh yeah, I remember her talking about that. Okay, that's what's going on here. So hopefully this was helpful.